All right, you guys, happy Monday. I apologize. I did not realize that I was going to be out of the building this morning, so I am just recording a quick lecture for you. We're starting to wrap up our geosphere unit. So today you should see presentations from your peers on solar nebular theory and the history of the Earth. And I'm going to just give this short presentation to you on the planets so that we've got all of our bases covered. Make sure that you've written down your guiding questions in your notebook so that you can follow along as we're moving through this presentation. So we're going to be talking about planets. Specifically, we're going to be talking about the Earth because that's our planet. So obviously that's the one that we're kind of the most interested in. And you're going to hear more about how our solar system formed and how the Earth formed and the history of the Earth from the other presenters today. Planets form from all of the leftover gas and dust within the solar nebula. So 98% of that material is hydrogen and helium that just never really amounts to anything. But inside of this line called the frost line, rocks and metals can condense because it is a little bit of a higher temperature. And so the hydrogen gases stay as gases. But beyond the frost line, it's much cooler, and hydrogen compounds and metals and rocks start to condense. And so the composition of things beyond that frost line is going to be very different from the planets that are inside the frost line. And when we take a closer look at our own solar system, we'll sort of see how that plays out. So to take a closer look at what's going on here with planet formation, we can consider the following flowchart. So for terrestrial planets, such as Earth or Mars to form, we see gases condense into rocky particles. So it's too hot still for really, really small gases like hydrogen and helium to condense, but our larger gases and our larger elements start to condense into rocky particles, and they gradually begin to clump together and they start to accrete more and more. And accrete means to accumulate over time and to grow larger through that accumulation. And a lot of these interactions are due to very, very small interactions due to gravity. And so the clumps form planetesimals, so very small little planets, and they just slowly accumulate more and more mass until we eventually have a terrestrial planet, such as Mercury, Venus, Earth, or Mars, for example, within our own solar system. The formation of a Jovian or a gaseous planet, also called a gas giant, is very similar. But in this case, the gases actually all condense into icy particles. So instead of being kind of rock-like, they form more of an ice substance, and the ice begins to clump, and those accrete more and more and form planetesimals, and then the Jovian planets are formed. This includes Jupiter, Saturn, Uranus, and Neptune. And so the process is really, really similar. The difference is just what temperature it takes place at, and that defines how the gases begin to condense. And then after they've started to condense into little particles, gravity really takes over and they just accumulate matter over time. The International Astronomical Association has requirements to be a planet. And we all know that Pluto got demoted from planethood a while ago. Then we sent up a deep space exploratory satellite to take a peek at what was going on in the outer edges of our solar system. It was probably pretty insulting to Pluto. But anyway, the requirements to be a planet are pretty straightforward and simple. The first thing is that you have to orbit the sun. That's kind of a no-brainer. The second thing is it needs to have sufficient mass to assume hydrostatic equilibrium, which is a very fancy way of saying that it's basically a sphere. It's pretty much round. So if an object in space is very egg-shaped or awkwardly shaped and not spherical and smooth, then it's not really in the running to be considered a planet. Lastly, the planet needs to be big enough to have cleared the neighborhood around its orbit. That means it's going to be the only large object in its own orbit. So Earth has a moon that orbits the Earth, but there's no other objects in the Earth's orbit. We don't share our orbit with anything else. And that is actually the criteria that Pluto did not meet, is that it didn't clear its orbit. And as we learned more and more about the outside edges of our solar system, we came to realize that if we were considering Pluto a planet, then there were about 30 more planets at least beyond Pluto that were very small, were roughly spherical. They pretty much orbited the sun, but they didn't have these really individual orbitals like Earth and Mercury and Jupiter do. And so that was the defining factor. We decided to kind of demote Pluto and change our criteria instead of having like a bazillion planets in our solar system. So in our solar system, the basic breakdown of our planets is as follows. On the left, you have the inferior planets, Mercury and Venus. And then to the right of the Earth, you have the superior planets, Mars, Jupiter, Saturn, Uranus, and Neptune. There's really no good reason why they're inferior and superior planets. It has to do with their relative location to Earth. So inside of Earth, they're all smaller than Earth, and they were named the inferior planets historically because of that. And then outside of Earth, they're much larger, and so they were called the superior planets. It's not that important to know, but it's kind of interesting. The other piece that's pretty fascinating is that there's that asteroid belt between Mars and Jupiter, and all of our terrestrial inner planets to the left of that asteroid belt, closer to the sun, are made of solid rock. And to the right, beyond the asteroid belt, all of the planets are basically Jovian gaseous planets. And that has a lot to do with what I was talking about at the beginning with the frost line when the solar system was forming. So the solar nebula with the sun starting to form in the center and all of this other dust and debris out on the edges, that frost line determined whether or not terrestrial or Jovian planets formed. So that's an important distinction between the inner and outer planets. The asteroid belt is a nice demarcation of that quality. So obviously in this class, we're really going to be interested in studying the planet Earth, but it's really nice to know about the context of the Earth in our solar system as a whole, and looking at the formation of the solar system at large can help us understand some of the things that happen on Earth that are a result of its formation. I hope you enjoy the other presentations today, and I'll see you guys tomorrow.